Welcome everyone to today's seminar. Sorry for the delay. Had some technical difficulties, but uh, today's seminar is going to be on TQFT and category theory. It's mostly just going to be a category theory talk. Going to go through the basics and make my way to hopefully braided monoidal categories. Um, this is probably going to be the first lecture in a lecture series, and um, yeah, I was trying to find resources to base this talk out of, and I came across this lecture series by Lucas Muller, and it's amazing. Here's the link to the course, and I just decided to base it off of that because I think has great pedagogy and the story flows nicely. So uh, mainly just gonna this is gonna be my main resource. And here's the table of contents. First, we're gonna motivate TQFTs. Then we're gonna go into category theory quite quickly and just make our way up to the toolkit that we need to do TQFTs. Um, Please feel free to interrupt at any time for any questions, comments, or concerns. So, why should one study TQFT? Well, uh, in QFT, a lot of stuff is not completely rigorous or well defined, and well defined in most cases is a nice way of saying it doesn't exist. And so TQFTs is one way that we can do stuff rigorously. And there's a lot of motivation in physics for why to study TQFTs, but this is mainly going to be a math talk, and um, maybe there will be applications later on, but like applications to physics. But for now, we're mostly going to focus on the math. Now, I've been told that in math, TQFTs can be used in stable homotopy theory, modular tensor category of fusion categories, how to get higher category theory, finding topological invariances, and so on. I also recently was told that it can be used for distinguishing smooth structures, which is really interesting. So I'll try to provide a motivation besides what I just said to why we should study TQFTs. In quantum field theory, we have the following things. We have a spacetime, which is a Riemannian or pseudo Riemannian manifold with and it has a metric, and we also have fields, which are elements of Fm, and Fm. For our intents and purposes, we'll take it to be C infinity maps from our manifold to some field. Our field is usually K denotes C or R. Usually in physics, we like to work with C or R. It can be other fields as well, but for our sake, we'll just take this. More generally, you can take it to be a principal G bundle with a connections of a principal G bundle, but to make our lives easier, we'll just stick to this example for what is Fm. And so also in QFT or in physics in general, we usually have an action that is a map from Fm to the reals. And here's an example of an action that you've probably seen in your physics courses, that you integrate a top form, which is your Lagrangian density form, over your manifold. And now you have that in classical physics and also in quantum physics. In quantum theory, you would like to compute the, I don't know why I'm blanking on the name, but correlation functions. There we go. Correlation functions, and this is how the physicists usually do it in a second course on quantum field theory, where this is the partition function, which I wrote is here. Now, you can just take this as a black box where we're not really going to focus on this in this lecture. just take this as a definition if you wish. Um, so you can put a colon here for this, and this has some problems. It sometimes ends up not being a well-defined measure, or sometimes just infinite dimensional, and it's not nicely behaving. So um, that's why we kind of want to make our way to TQFTs from QFT. Now, um, here's a definition. We want to talk what does it mean for a theory, for a physical theory to be topological. Now, in math, you can have different definitions for what it means something to be topological. It can be invariant under homeomorphisms, homotopy equivalence, or other things. But this is what it means in physics. So, uh, a theory is topological. I'm just going to abbreviate a lot of things for the sake of time. I'm going to say them when I speak, but just going to abbreviate when I write. Also, independent of the metric. That's another way you can put uh, what it means for the physical theory to be topological, if and only um, if you take variations of your correlation function, which is what you want to compute in a physical theory, with respect to the metric, it's zero. So it's independent of the metric. This is what it means for a physical theory to be topological, independent of the metric. Now, I'm going to give an example of such a theory. So when we usually say theory, it's another word for an action in physics, usually. If I have, this is the Chern-Simons action for an A is a connection. I'm going to define it as trace of A, which A dA. There we go. Should put example. Right. End of definition. And okay. Yeah, so for this, there's no dependence on the metric. And that's, I guess, a concrete example. Now, here's a proposition. Yep. S phi, how does it depend on G? This is the Lagrangian, yes, and the G is used in the Lagrangian. Usually, explicit example is this: G mu nu, I die mu phi, die nu. To take the inner product, you use the metric, and this is an example of an action or a Lagrangian density. Exactly, a theory is specifying an action. There are generalizations of this when you just talk about symmetries. We'll hopefully get to symmetries in a bit, but that's a good pedestrian way to think about physical theory. It's just an action. That's for abelian gauge theories. These aren't forms, so uh, I don't want to get into it, but I'll get into it because you asked. So A is okay. The gauge theorist here, please correct me if I'm wrong. I'm a bit rusty on this, but it's sections of a the endomorphism bundle on some total space E tensored with first alternating wedge of T of the cotangent bundle. Is this correct? A, yeah. form.
Yeah, again, well, they're not necessarily sections but they will be maps. So they will be a map from E into the tensor wedge.
I see. I see.
Yeah.
I see. I see. Okay. Okay. Right. Yes. Yes. Now, I think that's captured. I could be wrong, so I'm gonna say this. I think that the map that you mentioned from E to the space is captured by the endomorphism bundle. But I haven't worked with these stuff in depth, and I'm rusty, so I don't really remember this stuff well. Um, but but yeah, I think it's a map from your entire space to um, sections of your entire space tensored with alternating wedges of the cotangent bundle. So it's something similar to this. This could be wrong. Uh, that's why I'm going to erase it. But um, the thing is, you shouldn't think about pedestrian ways that you shouldn't think about these A's as one forms. Think of them as matrices of one forms. So and the wedge, what it means when you take two matrices, you do matrix multiplication, but each entry that you're multiplying, you do the wedge product. So yeah, okay, that's a good you're welcome. That's a good pedestrian way of thinking about it. Now the technical details I don't know off the top of my head. Sorry. Okay, so here's a proposition. Um, so I'm gonna talk about the Hilbert space associated to some sigma. Now, this isn't necessarily a Riemann surface, but some well, what it is usually a n-1 dimensional um, submanifold, right? And this usually ends up being time slices in a space-time manifold. So just think of it as that, where we're gonna see that there's gonna be boundaries of some cobordism later on. I want my Hilbert space associated to this submanifold to be, I'll put in quotation marks because it's not exactly equal, but we want it to be equal to L2 functions on my fn's. I want it to be that. Okay. Now, so I'll take the Hilbert space. I have to work on my math cal letters of the disjoint union of sigma and sigma prime. What is this going to be? It's going to be, if we take that to be true, O2 functions on the f of sigma, disjoint union with sigma. And so now, what is this going to be? It's going to be two functions on the Cartesian product of these two fm's, f sigmas. And this ends up being the tensor product. So this is very heuristic. We'll get to making this more rigorous later when we learn about the what kind of a functor TQFT is. But for now, that's why I put in quotation marks. We want this to happen. I didn't close the quotation marks. Yeah. This is going to be L2 functions on sigma tensor L2 function on sigma. And that's going to be isomorphic to the tensor product of Hilbert spaces associated to these submanifolds. So what's happening is that if I have two disjoint, the disjoint union of two closed submanifolds that they'll usually be, I want the Hilbert space that I assign to this entire space to be the tensor product of the Hilbert spaces assigned to each one of those. This is what I would like to have, because in physics, we usually, if you've taken a quantum mechanics class, you always want to have some Hilbert space associated to your space, meaning your manifold usually, to be able to talk about states and do quantum theory. So, but this is very heuristic on purpose. It's kind of just an overview. So, should put section 0. And okay, I'm going to draw a donut now. And I'm gonna cut this donut up to sections. And well, I shouldn't say section. Parts, let's say. And I wanna draw a math cal M1. Put this as 2. And M4. So, such that the entire thing is M, my manifold, and it's going to be 2 sigma 3. Yeah. So what I did here is I wrote my manifold as some gluing of some separate manifolds. Now, my manifold itself is a closed manifold. It doesn't have a boundary, but I wrote it as the union with some gluing action going on of some manifolds with boundaries. And we want to see that it doesn't matter how we partition our manifold, meaning what the things it consists of in terms of gluing different manifolds together. We want our gluing, we want whatever we come up with our theory to be compatible with this gluing of different manifolds, and talk about that more in depth. But yes, there's a question. Oh, space like separate. Uh, so you mean like here? So okay. Um, I would just say, just take sigma for our intents and purposes as n minus one dimensional closed manifolds, and this is just the disjoint union of them. It'll end up being that there's a smooth embedding of our sigmas into this manifold, as you can see in this picture. They end up being um, the boundary of each one of these different manifolds. But yeah, mathematically, just think of it as what I said. Now, physically, I really haven't thought about it much myself, so can't really give you a very satisfying answer because here, because I mentioned their time slices, but I don't want to get into that because I'm not an expert in it, and so yeah. I should have clarified as a disclaimer at the beginning that I'm no expert on any of this. Doing this to learn this stuff as I explained it. So physically, we'll think of this direction as the time direction, and if I go below the camera point, tell me. Um, but yeah, so okay, yes. So, uh-huh. It's square integrable functions um, here. So, yeah, yes, yes. Let me think about it. Okay, so, um, uh, right. This is the space of, well, I guess uh, more precisely, I'm taking elements of this. This is the space of C infinity functions from your manifold to your, let's say C for simplicity. Now you're taking a function from your manifold to C, and L2 just means it's square integrable. So you're integrating that function with its um, complex conjugate over your uh, your your manifold. So you have to have some volume form, as you mentioned, right? Um, I think if you write it in forms, it's probably gonna look something like F wedge star F, such that it gives you a top form. I think that's what it's gonna look like, but I don't know. Sorry. But it's a good question. I didn't think about it when I was thinking about this stuff. And that's one of the reasons why I wanted to give this talk. Stuff that just go over and think, oh yeah, it makes sense. When I encounter good questions like that, it makes me stop and think. So appreciate the question. And this is the empty section. Okay. Right. So let's analyze these individual parts that I cut up my manifold up to separately. M1 is going to be this is my M1. Yep. Uh, well, I'll put the. It's fine. This is my signal one, and this is the boundary of my M1, and so my partition function on this manifold that we talked over there. I want this to be an element of the Hilbert space associated with the boundary of this manifold for physics reasons. And as we said, I want this to be L2 functions on F associated to this submanifold. And so what this does, what my partition function does, is takes a phi uh, associated with sigma 1 and spits out what I have there, that expression with the integral. So I'll just write it down because it'll be easier. It takes phi associated to sigma 1 and it gives me this integrated over phi's, which are elements of f on my manifold, e to the minus I s phi. This is what it's going to do. My my partition function. Now, um, mm, yes, probably. But this was a typo, yeah. Because yeah, that doesn't make sense. This is going to be some numbers, so it's probably there's a d phi there. Yeah, has to be. Uh, this integral. Yes, that's true. True. on no, it's M1, and such that when you restrict the phi's to the boundary of M1, you get phi of sigma 1. Stokes theorem? I don't really. Maybe.
So it takes the thing on the boundary,
Yes. Yes. Yes, you have to restrict it to the boundary, yes. I should write it down here. Such that phi restricts to the boundary of the manifold, which is going to be just phi. We denote it like that. Well, you think I'm going to write the other parts there? So, then there's a pair of pants here. This is my M2. And what does the partition function here do? Well, remember, this is my sigma 2. These two, the disjoint union of this and that are my sigma 2, and this is my sigma 1. And what does my partition function on this manifold do? It takes in, well, my manifold, and so, okay, so the partition function associated to this manifold, what it does, it's a map from my Hilbert space on sigma 1 to my Hilbert space on sigma 2. And how it does this is takes functions of something that are elements of my sigma 1, and then the should write it down there to make it so I can write it element wise. Let me erase this. Z of 2 goes from sigma 1 to sigma 2, and this element wise is going to be functions that take in something in sigma 1, and it's going to map it to maps between phi at sigma 2 to the integral thingy. I think if I write down the whole thing, it's going to be kind of time consuming because we also started it. You know what? I'll just write it of phi restricted to this that side sigma 1, and you're integrating over phi on elements of f sigma manifold, and you restrict to the second. You restrict your phi's to the second, to sigma 2. But I don't think this is very insightful. I think this is just confusing. And it's just my inability of explaining this properly because I don't understand it fully myself. But the thing we're trying to get to, which is the important thing, basically I'll just chalk this up to there are some things in quantum field theory you want it to be true, and what it leads us to is going to be this part. I'm going to write it down. When I was writing that down at like 3 in the morning, it made sense in my head, but now it doesn't. So, I want to see what the composition of my partition function on my third manifold with my partition function on my second manifold is. And you can go through the same detail I wrote there, but with the opposite pair of pants, the inverse pair of pants, and yes, yes, exactly. Yes, that's true. Right. Yeah. Yeah. Okay, but what I want to happen is that uh, I have this, and it eats something and takes in a phi of sigma 3. Gonna box this. Right. This takes in that, and then this composed with that takes in that. This um, ends up being, when you go through the details of the integrals, I'm not gonna actually. There's a lot to write down, so I'm not gonna write it. You get something e to the I, uh, the action on the third manifold plus action on the second one, and this is due to multiplication of exponentials. You can write it as um, addition in the exponential itself. So this is just a basic property of exponentials. And what this gives you is that, so I'm just going to write it as a result here. Three, two. And this composition, we'll see later on why I wrote it in this way, but it's when I glue those two manifolds together. That's what it's saying here. Is going to be 3 So yeah, the composition of these two manifolds, if I take the partition function, is going to be the composition of the partition functions. And there's a whole lot of detail that I just skipped. Sorry about that, but essentially, I'm just going to say, trust me, when you work out the details, when you compose these two partition functions, you'll get a multiplication of exponentials, and you can write as one exponential of the sum of these. And so this is the result that we wanted to get. Now, okay, this was the compatibility with the gluing that I was talking about. It's what I wrote here. So let's think of a definition for a TQFT. This is gluing, right? Gluing nicely. Nicely is Shouldn't go into the details of the topology, but yeah, what it means, I'm gluing M2 and M3 together nicely on the boundary. And yeah. So we'll see later on, probably in this talk, but in a later talk, why I wrote it as a composition, but it's just the gluing. And this is just composition of functions for the z's. Yeah. Okay, so now let's try to come up with some definition. I'll put a question mark because this is not the definition, but it's us brainstorming. So I want a n-dimensional TQFT to have the following. I want a Hilbert space associated with my sigmas for all the compact-oriented n-1 dimensional submanifolds. I want to have that Hilbert space associated with those spaces. I also want to linear map my partition function from Hilbert spaces on sigma to Hilbert spaces on a different sigma prime, let's call it. For all the cobordisms, which is a map from sigma to sigma prime. It's a manifold that maps from one sigma to the other one. And I'll write it down. So that is a cobordism right there. It's a map from sigma 1 to sigma 2. And I want the Hilbert space on the disjoint union of these topological spaces to give me the tensor product of these Hilbert spaces, each associated to their own topological space. And also for, I want the Hilbert space associated to the empty set to just be my field, which we'll usually just take to be the complex numbers. So I mentioned that. I can write that down, but I just explained it, and writing it down I don't think is too insightful. I just want Hilbert spaces assigned to the sigmas. I want a linear map between my Hilbert spaces assigned to each sigma, and I want my Hilbert space of the disjoint union to factorize nicely to tensor products of Hilbert spaces, each assigned to each space. So I might as well just write the proper definition, which was given by Atiyah. So I'll remove the question mark, put colon here, and this definition was by Atiyah. A topological quantum field theory is a symmetric monoidal functor Z from the category of cobordisms to vector spaces. Now, the reason why I'm not putting vect instead of hill, apparently there's some profound reasons in category theory that the category of hill is has some weirdness going on that I don't know anything about. I heard about it recently. If anyone knows more about that, please welcome to share. But we're just going to take it to go into vect, the category of vector spaces instead of Hilbert spaces. So yeah, it's going to be finite dimensional and also ignoring the inner product. Yes, math calendar. Because I guess just notation. That's our uh, mhm. No. I think it's for all different. Because what we care about are our sigmas, and we can have different m's cobordisms between them. So we want it to be for all of that. It depends on a fixed m. Well, it. Mhm.
I think like the TQFT could
I was under that impression that it's the full Buddhism category. I could be wrong. I honestly didn't think about the notation till you mentioned it. The axioms of these. Yeah, this is the definition. This is that. Yeah. So now you guys can say I know what a TQFT is. Modulo definition of a symmetric monoidal category, and maybe also the category of Buddhisms and category of vector spaces. So, sorry. Dimension for what?
for your TQFT.
Not yet.
So this is all manifold, every single manifold.
Closed manifolds. So compact, boundaryless manifolds. What was the second part?
So all of your closed manifolds you can put into one category.
I believe so. That is.
So you wouldn't have multiple
Ah. So for that you have to do the higher category theory stuff.
no, you just have like a district because like
Uh-huh.
you could have two
So okay. Yeah, I don't know much about that, but what I've seen is that um, we have our I'll write it. Yeah, here's good. So yeah, we have our whatever district union of things, and we have this, right? And so our cobordism is a map from the district union of these to the district union of these, right? It's a map from here to here, and so this is from an n minus one dimensional manifold to n minus one dimensional manifold. The cobordism itself is a n dimensional manifold. Now, so these all of these are just the boundary. If we don't think about orientation just yet, just the boundary of this manifold. Even with boundary, it turns out to be true, but we'll talk about boundary later. Sorry, orientation. Orientation. You want to fix n? Oh, yes. Oh, right. Yeah, I guess for n has to be fixed. N has to be fixed. Right. I think. Oh, I see. I see. I think I misunderstood. I was going somewhere else. Right. Appreciate it. I was gonna talk about that these are the boundary of this, but the boundaries can have boundaries. So corners, codimension 2, right? These are codimension 1, then we can talk about codimension 2, codimension 3, so on and so on. And these, it gets into the higher category theory stuff, which I don't know anything about. Yes. So I misunderstood it slightly. But yes, thank you. So yeah, of n, which is the dimension of this cobordism, should be fixed. I've not seen it not be fixed. Okay. I don't know. I'm gonna for uh, I'm gonna say no for to be conservative. I haven't seen it be can be infinite dimension. I think it's only restricted to finite dimension. I was worried I was gonna run out of material. I wrote like what 16 pages, yeah. Definitely not gonna run out of material, which may be a good thing, a bad thing. I don't know. Okay. Okay. As I said, now you know what the definition of a TQFT is, up to all these definitions inside of the definition. But this hopefully serves as some sort of motivation for why we want to study TQFTs. And what this tells us is that we should study category theory. It's very good. It's very useful. If we want to do this stuff, we should know category theory. So now, just going to give a crash course on category theory for people who know category theory. This will probably be boring, but I can't assume people know category theory. Probably most people don't. So that's the end of the 0th section. Now we're getting into section 1, which is monoidal categories. So let's start with the basic definition. Definition 1.1. It's going to be a category, and I'm going to abbreviate a lot of stuff for the sake of time. MathCal C consists of a collection of objects. So just going to write X, Y, and so on, that are elements of C, and a collection of morphisms, F, G, H, so on. We can put C here because we're going to use it, which are going to be in this category. These are going to be homes between objects. So basically, what we're saying is that how we study math, it's made out of things and maps between things. Those maps can be mapped to other things and maps between those things. And you can map those maps together and go on and do crazy stuff. And but that's like the gist of it. Okay, such that for all f, there's a unique domain and codomain. That will denote with source and target. F is going to be a map between objects x and y, and so we'll say that the source of f is x, and the target is y. Of f is y. Target of f is y. Okay. And we always, when we're defining categories, we want there to be some composition rule of our morphisms. So I want for all f from x to y and g from y to z, my composition of morphisms to go from X to Z, such that G composed with identity on the source of G to be equal to the identity at the target at G composed with G. So what does this mean pictorially? Looking at the right definition. It feels like it. I feel like I skipped something, but oh, I wrote it over here for some reason. That's yes. I don't know how that happened, but thank you for catching that. I was like, why am I talking about identity? Like, yeah. So okay. Yes. I have that for some reason after that. I guess this is what happens when you write your notes at 3 in the morning. So, okay. Yes, I'll do that. So just erase this. So it's associative and okay. Yeah, you have that. You want HOGF to be. This is your, and H is mapped from Z to something to V. So yeah, brackets don't matter, and we'll talk about when we get to more category theory stuff. We want to have this condition that brackets don't matter. Okay, have that, and for all X in object in my category, there exists an identity element denoted as this that maps from X to X, such that now what I was writing composed with identity on the source of G to be identity at the target of G and composed with G and it's G. So what does this mean pictorially? This line here, I have my G goes from I said Y to Z, and I have an identity that maps from the source of G, which is here Y, to itself. So it looks like this. This is identity on Y, or the source of G, which is Y here. And this is the target of G. Identity on the target of G, which is Z. This diagram commutes. Basically, if I do this first, then that is the same as I do this, then that, which is equal to this. All of these are telling you the same thing. So you don't have to worry about all these different compositions with identity. It doesn't do anything very meaningful. Okay. Any questions? So there's a bunch of examples that I think are useful for getting well acquainted with categories, but just judging based off the audience's facial expressions, looks like half of the audience is bored because this is too trivial. Correct me if I'm wrong, but so I'm just gonna mention the examples. An example is the category of sets. Now the objects are sets and the morphisms are functions. And what about the composition rule that we mentioned? Well, the composition rule for our morphisms is just the composition of functions that you know from like kindergarten or whatever. And I can write this down, but I don't think it's too insightful, so I'll just say them instead. If you really want me to write it down, please tell me. The category of vector spaces over some field F, the objects are vector spaces and the morphisms are linear maps. So when you were studying linear algebra, this was what you were doing. And the composition is just the composition of linear maps. That's it. In if you write it as a matrix, you just multiply matrices, and the reason why they're so weirdly defined, matrix multiplication is such that it works as a composition of maps. So there's the category associated to groups. Maybe it would be nice for me to write this down. We denote it as BG. It has one object, which I'll write like a singleton, just an asterisk, and the morphisms in this category are just acting on that with the group elements. So let me write this down. The morphisms on my category associated to groups is, and I apologize if my mathcal capital letters aren't really nice. So what this does is that one element that we mentioned, the object is just one thing, asterisk, goes G and H here are elements of the group. So and how am I acting on this? I'm just doing group multiplication. So okay, so no, for H G, this composition of maps, sorry, I misspoke, is defined as H times G, where this times is the group multiplication. And the identity element on these objects is just the identity in the group E. So here are some examples of categories, stuff that you're probably familiar with, that now you can see them from the perspective of category theory to make you appreciate how you can generalize these concepts. Yes, 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 yes. Thank you. Yeah, it's a good example because it's no functions. Yeah, I guess it makes you appreciate it more even. Yeah, very nice. So, um, okay, let me give you a definition of what it means to be an isomorphism. Should I erase this? Yeah, I'll erase this. Okay. C is a category. I'm probably going to stop writing it at some point. Just know MathCal C and MathCal D are going to be categories. And I have a morphism F that goes from X to Y. And again, for if you want the complete notes, I'll upload these on my website. So all the things that are abbreviated or details are skipped, you can read them. Yes. 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 For sure. Those are going to be the most important categories for us. So, yeah. Okay. So if is an isomorphism, if and only if there exists a f inverse from y to x such that these compositions give me the identity, and also this but identity associated to the input. So f takes in x, so the identity is going to be x, so it's going to be a map from x to x. F is going to go from x to y, then f inverse is going to go from y to x, so you go from x to x. And but it's not just any map from x to x; it's the identity. So this is what it means for one of our morphisms to be an isomorphism. Now, next definition, a groupoid. Didn't number this one. Okay. C is a groupoid. I spelled that correctly. Okay, nice. Or at least I think I spelled that correctly. So all my hums, all my morphisms from x to y, I want it to be an isomorphism. It's an isomorphism. For all x and y in my category. Okay. Now, here's an exercise if you want. If inverse exists, then it implies that it's unique. Something if you want to work on, but I'm gonna skip past this. Okay. Now I'm gonna talk about commuting diagrams, which I did a bit over there. This is a remark. It's gonna be about composition of homes. This is defined as this, and this diagram the proper thing would be for me to properly define H and K and all this, but you guys can guess that these are morphisms in my category from what element to what element. It's here implicitly. And also writing all this down would take time, but so we say a diagram commutes. This diagram commutes if and only if this composition equals this composition. So what is this saying? If I do F first, then G, it's the same thing as doing H, then K. So I get to the same. I go from the same thing to the same thing. That's all it's saying. And what we'll do is we'll at some point only try to work with commuting diagrams because they're nice pictorially and they tell you everything you need to know. Okay. So for the special case of this, an example would be for the category associated to groups. It's just that instead of X, Y, W, and Z, you just have one object, which is your asterisk, and the maps between them are elements of your group. And they commute if this happens. So I'm not going to write it down because it's a very, I guess, trivial case of this one. Yes, and the relation is that it's abelian. Yeah. For right. Yes. Yes. But the comment about this for the group category of groups, you were saying gives you a relation, which the relation being that, and yeah. For the category of groups, take like G and H, and then H and G. Yeah, I should have written. Maybe I should have written down instead of saying, but don't think that example is worth the time. Okay, how are we doing on time? Not horrible. Okay. So definition, functor. Okay, things are starting to get exciting. We're saying the words that we said in the definition of a TQFT. So that's always a good sign. Tells us we have stuff to look forward to. So C and D are my categories, and a functor from C to D. This is horrible. Is made out of it's made out of, if I act on a object of my category, it's an element of object of my category. It gives me something in the category that it's mapping into, and by gives me something in, I mean is an element of the objects of this category. Okay, and such that, no, not such that, no yet, but it also gives me a map from morphisms in C to morphisms in D. And more precisely, I mean, by morphism, I mean an element of harms in that category. So, harm in category C between elements X and Y for all X and Y in objects in C. But, yeah. So, it maps my F. Should have just written this instead. These are harms in my category from C1 to C2. C1 and C2 are derived by their objects in C. To it's going to be now. This is going to be an element of harms in this category that it's mapping into the target of the functor. D1 and D2. I feel like I'm going too slow. Such that erase this. There's our nice compatibility condition, which is our composition rule. So the composition is going to be if I compose two harms in C and I take the functor of that, is going to give me composition in harms in my target, which is D. Also, act nicely on the identity, and how does it? What do I mean by nice? I just mean the functor on the identity in C1 has to be an element, right? It's going to be the identity in the target. But like, what F maps my C1 into? F of F is in the harm set. Yes, it's a covariant. I was about to say, yeah. Yes, yes. I'll write it in a commuting diagram. But yeah, there's a notion of a covariant functor, which is what we have here. A contravariant functor, when it maps the morphism from your source to your target, category, it just flips the arrow of the morphism. That's what it means to be contravariant. In these lecture series, by Lucas doesn't define them. Maybe they're not. We're not going to be using that. But yes, that's a good thing to note. So yeah, I have my category C and my category D, and I have elements here, C1, C2, and I have maps between them. C1, C2. I actually do it right after that. That's good. And then C3. D1 goes to D2, goes to D3, and identity on C1. Functor goes from objects there to objects here. T on f of C1. This is f of C1, and f gets mapped to f of f via the functor, and composition rule is here in the diagram when we say the diagram commutes. All of these are f's. Functor. When we say this diagram commutes, it's telling us what each object is mapping into from according to the functor, and it's also telling us what each morphism is mapping into, and it's giving our composition rule for free in this diagram because it's commuting, meaning that if I do this composition, then map it with the functor here, it's the same as I map my morphisms here using the functor and compose here. And no questions. No questions. One of my physics Olympiad teacher told me if there are no questions, that's either a really great sign or a horrible sign. So I hope it's the former. Okay, so here's an example. I'll just say the example for the sake of time. Also, yeah, I just don't think it's worth writing it down. If I have the category of vector spaces on some field, for our case K, if I act on it with the forgetful functor, which I haven't defined, it gets rid of the structure that the vector space has and only thinks of it as a set. So the forgetful functor is a map from, for our case, let's take the category of vector spaces to sets. So it has the set without the extra structure of a vector space. And what it does to linear maps is the functor maps it into functions. So it forgets the linearity of the maps. There's also the case for functors from the category associated to groups to vector spaces. What this does, it maps your one element to a vector, and the homomorphisms G are going to turn into row of G, which is going to be a map from a vector space to a vector space. The composition rule is that if I act on the multiplication of G and H with my functor rho, I should write this part down because it's going to be hard to keep track of if I just say it. It's going to be this. And the identity in the category associated to groups is just going to be, if I act on it with the functor, it's going to be the identity on the vector space. You know this as a representation. in group theory or representation theory. Mm. Right.
Function of sets gives you
Yeah. Oh, that's very cool. Nice. Nice. Yeah, actually, I don't know if I've encountered that before, but yeah, very interesting. So, in the abstract, I made it sound like we're going to really play around with all these categories to build understanding, but I feel like I'm not doing that. It's also hard to do all of that in this time. Let's see. But yeah, feel free to give me live feedback. Okay. So, okay, here's a proposition that says there exists a category of categories and functors. There are some details about being small. That it just means the objects and morphisms form a set. But in this category, the objects that we work with are categories and the morphisms are functors. Now, it also has a proof. Should I go? I think this is actually a useful thing to go over. I should write it down. We shouldn't just say everything verbally. I should actually write stuff down. Proposition 7. Okay. There exists a category of categories and functors. So, uh, yeah, objects are categories and morphisms are functors. So, what's the proof for this? Okay. Let f be a functor from C to D, and G to be also a functor from D to something E, mathcal E. These are functors, and the composition of these functors nope, nope, not yet. The composition of these functors are going to go from C to epsilon. Sorry, E. My bad. E. It's a mathcal E. This is defined by. How do I define this? Um, so I take an object that f takes, which is going to be C in my category C, and this is just going to give me G of the target of f. So it's just going to be written like this. Now this is an object in D, and this takes it to E. And yeah, yeah. So it goes from, and also for the morphisms, I should just write it down. Don't bother saying. QF acting on the morphism, right? Because it's not just objects; it's also morphisms. This is the map. We write it like this. It goes from sources of my morphism to the target of this. Keep messing up my math counts. there exists a identity and it's associative, but these I'll just leave as an exercise. But yeah, so we can go a level higher in abstraction and just imagine our categories as and as categories themselves, and the map between categories are functors, and those become our morphisms and our new category. Okay. How we're doing it? We're almost done. I'm not even half done. Okay. No, it's fine. Said it's going to be in a series of talks, so I can just leave the rest for later. There's an example for functors between the category of categories to the category of groupoids. Should I go through this example?
Oh, you just take the invertible morphism. Okay.
Oh, that's what it's called. Yeah,
That's
that
like
makes sense. I see, I see. Okay. There are a lot of examples here. Let me see which one is the most meaningful to do. Um, they're all equally meaningless or meaningful or meaningful. Yeah, the thing is, these examples help you understand the concepts that we're dealing with by giving you concrete examples of like, because this whole thing, we're just making the things we already know more abstract. So these help with that. But if I go through all the examples, I'm realizing that now that it'll take way more time than I initially planned. So yeah, yeah. Okay, let's see. Let's see. Um, right. Let's talk about the opposite category. Or does it have any other names? Dual category? Just opposite? No, dual. Okay. So let's just talk about that. Yeah, because from what I've seen, we don't really do that much with grouphood, so I can skip that. Invertible. Yeah. Okay, so example 1.9 in the notes. So C is a category, and I want to know what C op is. The opposite category, the objects are the same thing, so they have the same objects, but the morphisms are different. So the morphisms, instead of going from X to Y, they go from Y to X, Y to X, and the important thing is the composition rule, which is if I go from Z with G op to Y F op to X, this is the same as Z going to X of G O F op. So F goes from X to Y and G goes from Y to Z. So what is this? Is saying, okay, I'm gonna do GOF. What is GOF? Goes from X to Z, right? What is the opposite of that? Well, it has to go from Z to X, right? Z to X. How do I do that? Well, remember that the arrows get inverted. G op goes from Z to Y, right? So how do I get that? Is that I act on z with g up goes to y, then I do act on it with f up goes to x. So this is the composition rule. So if I write it down, it'll be f up g. Is that? Okay. Yes, because it reverses the maps. Oh, yeah. Oh, I didn't think of that. Nice. But yeah, okay. So we have this. Okay, natural transformations. Good. Now, I always said 2 hours. That's the hard limit, and I'm gonna stay true to that. And that's with questions. Does anyone have questions? Yes.
It's like F1 up.
It's just a reversing of errors. That's, yeah. And another thing that is really neat about category theory is just a lot of stuff you just say. You build the commuting diagram and the definition, and you say this thing is the dual theory. It just means that you just reverse the arrows. That's it, and you don't have to define it. So it makes our lives simpler. Okay. Um, a good example of this, let me actually write this down. This is useful. Is that this functor uh, goes from let's say vect to vect op. So element wise, it takes in a vector and it gives me an element of the dual, right? And what is the dual? So let me just write this. The dual is defined as maps from, well, linear maps from V to your field, which we take to be K. And I thought I wrote this down for uh, a natural isomorphism. Oh, I have that later, I think, between V and V double do. That should be later because I'm pretty sure I wrote it down somewhere. So I guess we'll get to that later. But I guess after we talk about natural isomorphisms, we'll see that V and V double dual are naturally isomorphic. And the natural isomorphism is given by you just act on V with an element of the dual. So you just act. Uh, um, let me just write it down. F of V, and this. So what is this? This is an element of the dual. Is a linear functional goes from V to K, and what does the double dual do? It goes from dual to K. So V double dual. I guess I'm doing the example now. V double dual is a map from the duals. So the duals are from V to K to K. Uh, and yeah, so yeah, maps from V to K to K. So this is V to K. It gets mapped to K. This is the double do. It's a map from maps from V to K to K. And how do you get that? You just act on V with your linear function. But yeah, I don't know why I did that just now. It's fine. What's the time? We got 5 minutes. Any questions? Yes. Okay, thank you. I guess that's the best question could have been asked in terms of getting through stuff. So I guess I'll just define this and call it a day. And for the later talks, we'll do the rest of it. And this is like the halfway point. 8 pages, exactly the halfway point. So, right. Let f and g be functors from C to D. And a natural transformation eta is maps from your functor to the other functor denoted with this double arrow thingy. And okay. It also has on this category C, it maps functors from acting on C to G of C for all C in objects. Such that so this is acting on the category C. And this is in C prime. I guess I changed my notation halfway through. Interesting. Okay. Okay. Let me just write this down and finish this. C prime. C prime. This is going to be F for all F from C to C for all from C to C prime. So this is hums in category C. Yes. F's are hums in category C. Yes. So both C and C prime are objects in category C, such that this commutes. Yeah. Yes. Very good. Yes. Just yes. Yeah. I won't write that. I promise to keep it under 2 hours. So exactly, and then you do infinity categories and yeah. But yeah. Now, if I want to give a continuation of this talk, what I'll do is define what a natural isomorphism is, and then do definitions about functors and natural. Well, the compatibility of natural transformations with functors. Is there to see next? After that, we'll talk about a monoidal category. Then do a lot of commuting diagrams there. It's just all going to be commuting diagrams. So I actually came close to a monoidal category. That's good. And then talk about functors there and natural transformations. Then we talk about a braided monoidal category, then a symmetric monoidal category, and then we do some over and under crossings with some diagrams that you've probably seen in knot theory if you've studied knot theory. And yeah, so yeah, a lot of the stuff I didn't get to, but that's fine. Um, I hope you found this useful. I certainly uh, learned a lot from these lecture series and also talk about this. I have to go think about some of the questions you guys asked. And yeah, are there any questions? But, but I guess to answer your question, no, I'm not sure about the infinite dimensions or not. Um, yeah, I kind of got mixed signals about that. I my wanted to say let's work with finite because it's usually nicer and stuff breaks down when we work in infinite dimensions. That's why I said that, but I don't know. Yeah. Okay. 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 Oh. Okay. Uh huh. I see. I see. I think what it ends up being is that this stuff is nice enough that you don't need the additional structure of an inner product to get some results. Um, kind of like how when you do GR, at least in Eduardo, how he presents GR is that he doesn't introduce the metric until the very last lecture of the differential geometry section. You can get a lot of stuff without needing a metric. So, guessing something like that is probably going on. That you can get away with without having the extra structure. But yeah, ultimately for physics, you usually do always want or need a inner product, at least in my experience. But yeah, any other questions? Yes. Yeah. Fun. You said fun. Fun examples, yes, but I won't talk about them now. The the braided when I work with the braided group, which is later in the notes, do some nice stuff with natural transformations there with the commuting diagrams. And then so at some point we'll just be doing commuting diagrams, and after that we'll even move past that and just draw pictures of braids, and and our proofs will consist of just under and over crossings, which is nice pictorially. But yeah, I hope you guys enjoyed it, or at least found it useful in some sense. Um, yes, yes. Which, yeah, another, I guess, fun example is the natural transformation of the Wudu. Yeah, thanks for attending the talk. Appreciate it.